Okay, before the break, we were started creating our own linked list. Um, I am going to start doing a new thing. If I don't hear from you at all, uh, I'm going to mark you as not having attendance. I'll send out word about that later. And I have a feeling nobody's on the Zoom call to actually hear me say that right now. The way the first class was going, but we timed that to hit this break point. Right before the break, we hit a bug, so it seemed like a great time to take a break, figure out why this isn't printing, and do back to the software. I mentioned everything should have a two-string method, but hopefully y'all noticed that we didn't put a two-string method in, so that's an easy fix, right? It's a node that is printing out, so here in our node class, we can just insert a two-string method, and the only thing we need to print out is that element. I don't think we even need that. Let's just print out the word. Just print out what the element is. We don't need any element plus an empty string. That will always work. I don't know if we've done that in class yet. For a quick example, if we just concatenate on an empty string, that will always give us something there. So now we have the two-string method. Print this. Then we print all our elements. And then we close the list. Is that what actually printed? Did that ever end? I guess we probably should print the lines. So print a line, because that didn't come out very clearly, but oh, I did forget an important thing. If current's not equal to null, we just print it out again. The same thing happened over and over and over again. So we need to do like we did here and traverse the list. Okay, that runs. There we go. Something went wrong. So we're hitting little bugs. Y'all know the process, but the basic idea of how to fix it, build our own list. So it added the first one. If head is null, it becomes element. Afterwards, head's not null. So when we get to the second one, it should go in here. Start with the current. Go until we get to the very end, and then add that. If the current's not null, go until the very end and we'll print that. We look at our output, it's like something got cut off along the way. So I'm going to add a couple echoes in. Let's go through some of the debugging process. We haven't seen that much in class. Print out an echo. So I'm here in the add method. So when we add stuff, say looking at plus current. And for some reason we never reach the end of it. Why did we never reach the end? Start at the head. Then go to the next one. Another echo in. It says it's added. So they should be in the list, so maybe they're just not printing them. Was oh, let me change that around before I do this. When we start building data structures, you'll probably see the issue already. We'll get there in a second. You'll find there's a lot of this going back and forth. So at this point, we can tell it's added, right? So we added it to the list here, and it should be added here. So the problem has to be in the print method. So I'll take these out. No need to keep those around. For now, the next up is plus current. Print it here. Let's see what this gives us. Next up is null. So we went to the head, but then there's no head dot next. So somewhere we missed something when we added it. Does anybody see what it is? We added it we saw it the other day quickly in preview. So what points at the next element? I'm changing this up a little bit. So if we just check to see if the next is empty, we'll keep going. And then when the next is empty, then we'll add stuff. Oh, whoops, current dot next equals element.
When we keep over this stuff.
Well, at this point, then element node has a next element. So the next that comes in here is going to be null. So we add a new null pointer at the end. And that gets our list in. I just wanted to go kind of slowly with that one. That's basically what all the steps we'll do to create a list. We got some specific things afterwards. Things we might be familiar with, maybe an index, right? Public, here we'd want to return one of our elements, right? So we need to return whatever our generic type is. Yeah. And then we'll pass in an integer in I. What we would normally call it anyway, right? And we start with our first thing. And while current is not null, yeah, and this time we want to return when we're on. See the difference on when we want the current one, when we want the next one. If current's not null, current equals current dot next. And if you hadn't realized it already, hopefully you're noticing about now. But basically, anytime you make a method here, you're going to copy and paste from the previous method, right? And when we get to the end, we'll return current, and really we just need the element from the current, right? We don't need all of the next features or, well, we could leave them in. It depends on the situation. Again, may have to come back and say, add a getter here. Or make this public. I'll just make this public to make it easier. Because the only place we are calling that from is here. If we wanted to write a class. And now that data still falls in there because the only place we're going to call it from is here inside of this class, and we'd still have access. I'm just going to leave that like it was. Make them public to make it a little bit easier to work with because we haven't seen that yet. And it's perfectly okay to do this. So the biggest difference is we need an and here, right? Well, the current, if the current thing's not null and maybe some counter int equals 0 and counter is less than I have no idea why I shorted it that way. Counter is less than I. We'll increment that. So we'll go all the way up until we get to that index. I guess we want to check that index explicitly too, right? So we'll just keep walking until we get to that index, or we hit something that's empty. And if we need to check then. So if current is still null, then that means we didn't get anything, right? Return null. And might as well show this. We haven't seen implied code. If that if statement runs, we'll never reach the line afterwards, right? So that is exactly the same as an if else. In case y'all haven't seen that at any point. I don't think we've seen it in our class. So we'll print out mml.get index 1. And that should be the 1.23, right? Oh, 2.72. Went one too far, didn't I? So counter is 0. If current's not null, we skipped right over our head, didn't we? So what we might want to do, add another condition in here if head dot next, or no, if I is 0. If I is 0, we can return head. Head dot element. So if they ask for index 0, we'll return the element. Otherwise, we'll just start at index 1, walk the rest of the way through our list. We'll put a 0 there too. It won't hurt to do one more time through the loop. And then we get the index 2 like we would expect to be working using list. So that's how they're all built up. Hopefully at this point you can see the general structure there, right? We have we're just looping through the whole list every time. So we start at the beginning and go until we get to the end. And then we get the index 2 like we would expect to be working using list. So that's how they're all built up. Hopefully at this point you can see the general structure there, right? We have we're just looping through the whole list every time. So we start at the beginning and go until we get to the end. So and to extend those into stacks and queues like we talked about is very similar structure. We'll just, we just remove them from memory. So I guess we should remove something, right? Might as well do one of those. So public, I'll do a void and we'll just remove it altogether. If it was a stack or a queue, we would want to actually return that element so we could use it. But to just remove it from a list, let's remove it by index. It's probably the easiest way, right? And we already have working with an index here. So copy and paste this thing that we know works. If I is 0, instead of returning it, what we want to do is set up a temporary node to hold whatever had next in it. And then we'll set head equal to head.next. I guess we don't need the temporary or to 10. I'm doing it that way to make it a little bit clearer what we're doing. We could do that in one line. Hopefully it's obvious how we could do that in one line. But for clarity's sake, we grab the next thing and just replace the head with that. Maybe even more clear, we set the head to null, and then we set the head to the temp back. Then down here, we'll just walk all the way through to the index. When we get to the end, we have the one we want. So actually that would be too far to remove stuff, right? So if current dot next, if the next one is empty, and we're less than, do you see how I moved that equality from, let me type that code again. That's another common one. That's why I wanted to do remove. So the first, on the first index, we were doing current and less than or equal to the index. So I want to check the next thing, which means we are one behind the index we're actually worried about. Current dot next would be the I that we're concerned with. So the equality moves back and forth between those. If it's not null, we'll go to the next one. When it is null, we don't have to do anything. If we get to the end of the list, it's we don't have to do anything. So we're only concerned about when it's not null. So we don't need an else statement there. And at that point, if current, I'll draw a picture again. So here's the head of our list. Then we have another element. If we want to get rid of this one, we need to check, right, when we find the one we want to get rid of, we need this pointer to just go to the next thing. So if the current one is not null, that means we found the index we're looking for, and it's a current dot next. Then what we want to do in our code is go to the next one. If current dot next is not null, then what's that current dot next equal to current dot next. I know everybody's seen me draw that picture a time or two. So there's what that picture looks like in code. If we don't want to point at this one, oops, should have my pen for that. Look. We were pointing at this one. So to get rid of this element, all we have to do is stop pointing at that and point at something else. And then garbage collection. Java has really, really good garbage collection, so it will clean it up the next time around. Why does it say there's an error?
It takes a while to refresh it, even if there's not.
Okay. I thought I hit save, but I apparently didn't. If you hit save, it will automatically refresh. But I apparently didn't hit save. So let's try that. S out MLL dot remove index 1. Sorry, I don't know why I put that in a print. And then we'll print the list in print list. Or whatever it was called, MLL. Remove. No, it did not remove. What did I miss? Let's try this. Did the head get removed? So if we remove the head, it worked. So really, we need to do that every time. Temp, or no, temp equals current dot next. Then the next one becomes null. And then we set it to the temp. Kind of hard to see why that didn't work, because it looked like our normal increment operations, right? But because of how it's stored in RAM, when it starts working with it and moving it around, and there's no math operations being done. So it doesn't have that assignment the same way the math does. So we do actually have to store it somewhere and then move it like we did up here. Now we should be able to remove index 1. So some common errors, it'll take some stuff that you might want to mess around with it some. Why didn't that work that time? Current.next is not null and counters less than I. Maybe I do need to go equals. Oh. Well, I made a typo in there somewhere and I do not see the typo. Take this if else out. I think I actually need to look ahead at this one, don't I? I see you shaking your head. Did you think about that, Grace? Yes. We need to look 2 ahead. So then we can go 1 further here. Then we'll go ahead. And then if when we get to the counter or the end of our list is more than 2 ahead, because then we can no longer replace it. if current dot next, so if we went out on this condition, we got to the end of the list, then we don't need to do anything. So if we go out on that condition, we don't, current dot next is not, we hit the end of the list, there's nothing to remove. So if it is like when we went out, when it is null, so when it's not null, then we'll switch it out. And that removed it. So you can see it's very error prone. There's a lot of back and forth things that can go, a lot of back and forth and a lot of thinking on these. You want to kind of go slow, work with them, pay close attention to what's going on. That is everything I wanted to cover about linked lists. There's a lot more. We can keep building things, but it has to do with customizing the stuff. And hopefully it'll make more sense next Thursday. Does anybody have any questions about those custom lists? Try adding a couple methods to that. A couple other things that you would want from a list. Maybe organizing them, putting them in order, swapping things out. Traverse the, we only traverse the list forward. Can you figure out a way to traverse the list backwards? Give something like that a try, just to get some practice. And I want to put one more data structure, which is going to go really, really quick to cover. And then we'll probably wrap up early this evening, much earlier than the other day. That way there's time to catch up on homework and stuff like that. More with data structures. We haven't talked about sets. We haven't seen sets at all. This is one of our most basic types of collections. Actually, that's most basic collection. There's really only one criteria. Sets only have one criteria. That is no duplicates. That automatically implies some things, right? We only have one type of criteria. We cannot duplicate any of the elements in there. So we can't make a list of 15 things that all have we can't make a list of 15 things that all have an element 2 in there. If we try to make we can do that as a list. If we're trying to do that in a set, we would end up with only one element in it. It'll get rid of all the other copies. Some implications of the things, or only having one criteria in there, is there's no order to it. There's no order to it. There's no indexing. There's no way to ask for a particular element. That's not how I spell the word for particular element. Which isn't really a problem, right? Usually when we have a collection, we use the whole collection, right? Y'all have built enough programs with arrays now that you've seen that over and over again. We bring up that for loop and we go all the way through it and do something with every element in that array. But indexing is, if we're getting into data structures, things like where we're concerned with how much RAM we use and stuff like that. Those are integers. Integers are 32 bits each. So if we have, I don't know, 20 elements in an array that would all be indexed, then that's 20 indexes that we don't need at 32 bits each. That's 640 bits that we're wasting. Almost 2/3 of a kilobit. Yeah, almost 2/3 of a kilobit wasted off an index that we're never going to use. And there are other things that have order, so putting things in order could cause problems. And this one isn't really a problem because in most cases, we would use the whole thing. Then the other thing about that is they are abstract, which like we saw with queues. So when we go to instantiate it, there is no, the right-hand side, there is no just generic set. So, yeah, let's just look at it in Java. I'll put it in the data structure one, the one we were working on the other day. We were looking at stuff. I'm not going to build a set. Let's just use a set. So, I'll try to copy what I was doing the other day. A couple line breaks, and then a label. So a set object. We already had something with S's, didn't we? I'll call this S2 because our stack was S1. And just like with queues, we can't say, well, I can import it now. Do that import, we can't say new set. Oh, it's Java. I'll follow the same thing we were doing the other day, but strictly typed. All we're doing here is printing it out to the screen. So we have already talked about that sort of using the particular data structure. But you'll see that set isn't an option here. Will the predictive text give me something? I don't think it will. Equals. Oh. Let me see if this will like try to automatically fix it. So over here. No, the only thing the IDE can figure out is to create the classes. So what we need, actually I should show you what that does. I'm going to undo this. So let me show you what it does if we do that. It says we need to instantiate all the abstract classes. So if we do that, implement all abstract methods, have to implement it from all of them and generate that. Notice that it did it right here. I'm going to undo that just to show you where that does it, because when it's a shorter list than set, sometimes that's an easier way to go. But sets have a lot in them, so I'm going to hit Control Z to undo that. And there are a couple options we have. We have a hash set, which we still have to talk about hash, what a hash is. hash set. Again, uh, still have to talk about what a hash is. We'll get to that very, very soon. Or we have a tree set. And a tree is definitely going to be on there Tuesday. And I think I was going to talk about hash tonight, but since we're already past 8 o'clock, it's going much slower than I planned for it to. It could be at this point about 10 till 8, but since we're already past 8 and we went late, that we went really long the other day, I'll probably push what hash is back to Tuesday as well. But we have to do these different things. So for now, we just have to create one of these. So maybe a new hash set. And then we can import that. Hash is just a really, really good way to store things on a RAM chip. And in an optimal situation, it gives us almost electrical speeds. Right? Processing is always going to be slower than electricity just moving through a circuit. So we'll see, we'll talk about that on Tuesday. And a hash check uses the hash code to check for duplicates. That's what all of these are, right? We only have one criteria. So the difference, a linked list is just like a hash set, except it stays in the order we put it in. A hash set will change orders. It's only using hash codes. And then it just reverses it's a linked hash set is the same, except that it stays in the order we put it in. So we do get order back from that one, but it's a little unreliable because of when it checks for duplicates. Does it which one of the duplicates gets removed? Right? Because if we put in a duplicate and then that duplicate gets removed, it's really not the same order we put it in. If the duplicate would have been, I'll use preferred index 5, if we were in an array, then it's the 6th thing we put in there. So it's everything after that is no longer in the order we put it in. So there is a little catch on that same order we put it in. Same order we put it in, but duplicates aren't allowed. So then the tree set sorts them if they're comparable, so we get a bit of an order. But we can't pull them. We can't pull out individual elements. We can grab the first one or the last one. We can tell what the first or last one is, but everything else is just in there. So we still have to get the same set. There's an order, but we only have access to the very first and very last. In general, it's not going to matter because you're just using a set whenever you want the situation where there's no duplicates. So here I need to duplicate some stuff. So like we saw the other day, we can S2, we can add it. This is our most basic collection, so all we have is add and remove. And I don't think we have as many remove methods as we do in some of the other linked lists and array lists and things like that. So we can add a 3, S2 dot add. What were we doing the other day? Words. Add in a string. S2 dot add a floating point number or a double precision floating point number. Talked about that little F earlier tonight. Then we'll add in a Boolean. Oh, actually, I'm going to add 3 again. I'm going to add 3 again. S2 dot add words again. S2 dot add different words this time. And as false. Now, if we loop through here, object S and S2. And then just print them out. That's probably enough. Yeah, hopefully no surprises there. The duplicates are gone. Um, and then we can remove stuff. This is a little bit different. Notice our options for remove. We have less than we have with linked lists. We have options on how we remove things. You can pass in an index or the object, but we don't have any indexes, so our only choice is to remove by object. So we could remove that object that says words. And then I guess to see that, we'd have to print it out again. Do words. And then print that out again. Those can be really, really nice because that's our smallest collection that's built into the language. So if we want to cut out some of the overhead, maybe y'all are well aware of that. Wrote enough code, usually if we have a collection, we want the whole collection. We're going to go through the whole thing and use an if else structure to see if it's the one we want. And when we find the one we want, we can just throw in the break keyword and jump out of the loop. Like here it is. If we want to start cutting out overhead, instead of doing like we were doing earlier this evening and making a linked list, we will this one is built in there and most of the overhead is already cut out. So before going through all the trouble of making a new data structure, I kept saying earlier tonight, that's a point in programming where we stop and think really hard about how we're doing it and what's going on inside the computer, what the best way to do it is. A question to ask is, will a set work? Will that most basic data structure that has as much overhead as possible already removed work for us? It's a good one. Try to work it into some of your code. Give it a try. There's not a whole lot of requirements on data structures in this point. We're introducing them, but it will be a big deal moving forward as you move forward with your careers, software development. Anybody have any questions about those? Okay. I assume 5 seconds of silence means no questions, which brings us up to well, this one's early, 25 seconds till 8:15, and that's the time I was hoping to wrap up because we went so long the other day. If you have any questions, let me know. There's gonna be some new issues starting. Well, I'm gonna stop the recording. Everybody stick around for a second. I want to say something after the recording. I will say in the recording, there's gonna be a new some new policies going. If I don't hear from you at least once, whether in the chat room or speaking, it's gonna make a difference on attendance. But otherwise, I'll see you on Tuesday. Everybody have a great weekend. Please stick around for 1 second. I'll try to stop.